In this work, we present cross-embodied co-design for dexterity, a framework which generates, designs, and deploys robot hands sim-to-real. Endowing robots with human-level dexterity requires advances in both fine-grained control and the design of highly capable robotic hands. Traditionally, these two components have been developed separately, which limits performance because control strategies are constrained by the hand's physical design. Co-design addresses this challenge by optimizing hardware and control together, but the search space becomes extremely large for complex, dexterous manipulation. We overcome this scalability barrier with a morphology-conditioned, cross-embodied policy and a modular, physically realistic hardware platform that enables rapid design-to-real-world deployment. Since the solution space for both control and design is large, prior co-design approaches have often focused only on locomotion in simulation with fast controllers. However, these control methods such as model predictive path integral and cross-entropy model control do not work well for long-horizon, complex manipulation tasks. However, generating one design and deploying PPO alone is not tractable. For each generated robot hand, approximately 47 minutes is needed to find sufficient control for each design when training from scratch. Over thousands of designs, this number well exceeds several days. By contrast, cross-embodiment allows for a single policy to learn how to adapt its control on a given embodiment. We show cross-embodied control and how realistic modular grammars can enable tractable dexterous robot hands sim-to-real with efficient search. Over all feasible design parameters tunable in MuJoCo, we found the hardware parameters of highest impact for improving dexterity. Over 12 parameter categories such as inertia for each component or length of each linkage, we deploy 100 sampled altered leap hands using Bayesian sampling. We then retrained PPO on each new generated design. Highest parameters of impact were all parameters that were well suited for co-design, morphology parameters and control parameters. This eliminated material properties such as friction, material type, and compliance from our search space, and allowed us to focus on morphology and control alone. We then aim to make our approach tractable for dexterous co-design sim-to-real using cross-embodied policies. First, we pre-generate randomized designs to train our cross-embodied policies. We test on 3 tasks including object flipping on the Z-axis with a fixed wrist, in-hand rotation, and object grasping. Each task uses randomized objects and domain randomization. We deploy in-hand rotation, sim-to-real using a blind policy with no camera or tactile in the system. This is shown for 4 co-designed robot hand sim-to-real. First, we generate 2008-000 randomized robot hands. To generate these hands, we introduce a parametric hand generator that creates large numbers of diverse, physically valid robot hand morphologies for cross-embodiment pre-training. The generator first samples palm layouts by placing finger bases around a variable radius circle and forming a convex palm mesh from the resulting grip points. It then samples each finger's structure, joint count, link length grammars, and fingertip geometry from a structured design space to produce richly varied morphologies. Every generated hand includes pre-computed collision geometry, realistic joint limits, and consistent kinematic representations, enabling scalable and reliable simulation. These hands are then to train a family-specific, cross-embodied policy for each task and saved as checkpoints for evaluation. The policy requires a morphology encoding in order to identify each design input. After cross-embodiment pre-training, we use a graph heuristic search algorithm to optimize robot hand designs for specific tasks. The method generates candidate morphologies using an epsilon-greedy strategy guided by a design value network that predicts performance without requiring full evaluation. Each iteration expands finger designs, scores successors with a graph neural network, and then evaluates the most promising complete candidates in parallel simulation while maintaining diversity across hand layouts. These results continuously update a lookup table and retrain the value network, allowing the search to efficiently converge toward high-performing, task-specialized hand designs. In order to deploy these designs sim-to-real, we developed a modular robot hand with modular electronics. This allows us to test a wide variety of designs by reprinting palms, finger lengths, and fingertips, and reconnecting them through modular connections. Finally, we deploy our designs sim-to-real for the in-hand rotation tasks by printing the generated design with added mounting for motor brackets and fine-tuning our control policy. We show the simulation results for the 3 tasks in simulation. In-hand rotation. Grasping. Object flipping. We search across 2,000 designs, as these tasks show little improvement beyond this point. For sim-to-real, we deploy on 18 randomized objects ranging from 8G to over 110G. All objects are unseen at test time, and the policy deployed has no state information, including no object position, and no tactile or visual feedback. The only observation is resistance the servo motor encoders detect when encountering the object. We show our best ranked design from the algorithm sim-to-real, compared to our anthropomorphic baseline robot hand with 5 fingers. We show 2 additional medium-performing designs to show additional designs generated by our algorithm, are able to deploy sim to real and showcase how design impacts task performance. Thank you for your time.